In this video, we're going to look at velocity, acceleration, and gravity, well, and other little physics things, but those are going to be the highlights. Okay, so there is this example. I'll let you pause and read it, but in there's likely some language that is going to give you a little bit of a hard time. You're like, distance, displacement, speed, velocity, acceleration. If you're coming from college algebra, you might remember these. Otherwise, it could be a little bit foreign. Okay. So let's just kind of talk about what these ideas mean a little bit first, and then if you need to do additional review, maybe go to your good friend Google and type them in, and then go from there. Okay, or ask us questions. You know, we like questions. What is distance? Distance. It's really hard to define distance without using distance. What I'm just going to say for distance is its total length of a journey. Oops, journey. Oh my gosh, U-R-N-E-Y. There we go. Okay, displacement, very similar to distance, but what we say for displacement is it's how far the object is from where it started. So you're kind of comparing ending to beginning. Okay. Speed is just how fast an object is moving. Okay. Speedometer in a car, for instance. Velocity is very closely related to speed, so it's going to be how fast an object is moving with respect to, this is the new part, its starting position. So like displacement, velocity, we care where we are. We are comparing where we begin to where we are, or where we end. Okay. Acceleration, nice easy definition of acceleration is how quickly an object's movement changes. Okay. So for distance, distance and displacement, the symbols are both D, so it's really awkward. Normally I just write out distance and displacement instead of using a symbol for them. But sometimes displacement, you can also call that position, and so you could, different notebook or different textbooks, different people use different notations. Some use S, some use P, some use D. It's really weird. So I'm going to use D for displacement, or sorry, D for distance, and then, or I'll probably just write out like displacement and then distance just to avoid confusion. For speed, we typically use the symbol S, and we compute speed by doing distance over time taken. Velocity, we use a V, and that's displacement now over time taken, mathematically. To compute acceleration, we would represent acceleration as A, and we would say it's either speed or velocity, one of the two, over time taken. Okay, that's the basic ideas of these physical quantities. Now for the diagram, okay, I left a lot of room for the diagram, I don't know why, but imagine we have the ground. For the example now, we're saying, okay, you, here's lovely you, I'm an awesome artist, not really, but anyway, you are throwing a rock, a ball, sorry, big difference there, okay, from a height of 4 feet, okay, and you're tossing it up, and it's going up at 20 feet per second, and then it's going up, and then it'll come down, and then you catch it again at 4 feet. Okay, that's the idea. When I start these problems, I usually have to translate it to a diagram just so I can see what's going on. Okay, one thing that I want you to keep in mind is when we're working with kind of vertical movement or vertical motion, we have gravity going on, okay? And makes sense, we're on Earth, okay? So gravity, when we talk about gravity, that's actually an acceleration. So it's a value of a. We call it g, and if we're in, so just pay attention to units. If we're dealing with metric units, it's going to be 9.8. If we're dealing with imperial units, 32. Okay. So now we're kind of getting to the questions that we were being asked in the exercise. Okay. So we want to look at, it said, what do you know about distance, displacement, speed, velocity, acceleration? Well, they all exist. That's what I'm going to say. They all exist. Okay. Distance is harder to compute because we don't know right now how high it went or anything like that, so we don't know its total journey. Displacement, that's actually an interesting thing to think about. Displacement, how far the object is from where it started. So if you toss it up and then later catch it, how far is it from the starting place? 0, right? Like it didn't, just comparing those initial state, the initial to final, they're the same thing, so it did not move according to displacement, which is really weird. Speed, it has some speed, right? It is traveling, but then velocity, because it is displacement over time, velocity is also 0. Okay, and then acceleration, we have acceleration due to gravity. Okay, all right, function for speed. Here's what we know. Okay, we know at release, it's going at 20 feet per second. Okay, then now if you can imagine throwing a ball up on Earth, okay, over time, the ball slows down, right? It'll slow down, eventually stop, and then come back down, and then it'll slows down, and then as it comes down, it'll speed back up. But anyway, so speed decreases. Okay, that's one thing we know. And then, like I said, eventually it would increase again. The other thing we know is that there is gravity, right? Okay, and okay, so now I'm thinking, well, I need to find a function, right? Well, I know that acceleration, we said that was speed. It's change in speed over change in time, right? Okay, and here's what I know. I know that A is going to be 32 since I'm dealing with feet, and then change in speed, I can represent that as speed final minus speed initial, so beginning and ending, or some other sort of thing. And then change in time, we can do like that if we want, or I'm just going to probably leave this as change in time. Okay. All right, so now, oh wait, I know a little bit more. Okay, I know 32 is equal to SF. Initially, it had a speed of 20, right, over delta t. Okay, and it said function for speed of a ball at time t seconds. So I really want to isolate SF. Okay, I can do that. I can say this is 32 delta t, and I actually forgot something. I'll come back to it in a second. SF minus 20. Now, the thing that I forgot, we actually need a negative here because gravity is pulling the object down towards Earth, and when we think about it in mathematics, when we go down on a graph, that's typically a negative direction. So we're just going to associate a negative with these. Okay, and then finishing this off here, I could say that, okay, we have 20 minus 32 delta t is equal to SF. Okay, and that really is my function that I wanted to find. Okay. Now, more generally, this actually generalizes. Okay, what we would see, we can use speed or velocity. I'm just going to write it in velocity. We would say velocity can be represented as a function of time by saying you have v initial plus a t. Okay, and the reason this is so important is think about our linear models. Okay, here, so this is our variable, right? Then we have our a and vi, right? A is our slope, and vi is our vertical intercept. So we have slope-intercept form, a linear model. Kind of fun. Okay, so this is a very important equation. We will see this pop up again, most certainly. For the second function, not going to worry too much about that right now. I'm just going to say for height, we can really think of that as displacement. And we can think of that as, if we wanted to use d for that, we could here. We would just say that this is, our final place minus, or in comparison to where we started. So final minus initial position, or height. Okay. And then all I'm going to say is it turns out that we can say d final is equal to d initial plus v initial t plus 1/2 a t squared. And so you'll notice that this has an exponent of 2, which actually means that this is a different type of function called a quadratic function. And we will see this over and over again in chapter 2. Okay, so be on the lookout for that. Okay, big idea here, just to reintroduce you to these, introduce, I should say, you to these 5 physical quantities: distance, displacement, speed, velocity, acceleration, and then get kind of a nice linear model out of this whole thing with velocity. They're using velocity, acceleration, and time.